Welcome to Extraordinary Concepts in Physics. Today we'll be talking about different aspects in gravity. I call it potpurri because these things didn't fit into any lectures. So this lecture is being given near the end of the course, and there's little slides and things that didn't seem like they would make up a full 15-minute lecture. So I put a bunch of them in here. So I'll be jumping from place to place here. Please bear with me, but it will be fun. There's some cool stuff here. So I am Robert Nemroff. This is Michigan Tech. And this is an actual class at Michigan Tech. I'm an actual professor at Michigan Tech, sometimes called Physics X. So you can find these lectures, lots of these lectures, online or on iTunes by following buzzwords that you might find there. So let's get to some physics concepts. Most of these have to do with gravity. So one is Birkhoff's theorem, which is really important. That allows us to do a lot of gravity and understand a lot of general relativity. So Birkhoff's theorem leverages usually spherical symmetry in general relativity and has two common applications. First of all, it says that outside a spherically symmetric mass distribution, one that's not rotating, the solution is always a Schwarzschild metric. So that's the standard kind of gravity that has a Newtonian gravity analogy. So you could have a star inside that's pulsating or has different shells of a different amounts. You don't have to know the details, according to Birkhoff's theorem. All you have to be able to do is declare that everything inside is spherically symmetric, and then outside you can use the Schwarzschild metric. Also, Birkhoff's theorem is useful as if you have a shell. So here you have a shell of matter. Inside the shell, supposing that all of this is spherically symmetric again, the gravitational field will vanish. So this is useful for ignoring the outside universe. So sometimes people worry what happens if there's an outside universe that is affecting us in ways that we don't know. There could be tremendous amounts of mass distribution far away in some directions. Yes, they could have an effect. But if the universe is smoothed over on some length scale, and you can say that past some length scale everything is infinite and uniform, then Birkhoff's theorem says you're justified in ignoring it. The virial theorem, a really key theorem in several parts of physics, in particular gravity. It allows you to estimate one type of gravitational energy given another. Specifically, the relation is between the average total kinetic energy of a system of particles and the average potential energy of those particles. I usually picture it involved in galaxies or in globular clusters. So in Newtonian gravity, it's written like this. However, for other force laws, it could be written differently. It's useful, for instance, for determining the amount of dark matter in a cluster of galaxies. Again, that's another system of points, particles. However, you can apply this even to one particle. One interesting thing is through the virial theorem, well, I'm reminded from the virial theorem that, for instance, elliptical galaxies have lots and lots of stars. Actually, we'll get into that in the next slide. So that's the virial theorem. This is the next slide, the gravitothermal catastrophe. This shows it's sort of a battle between gravity and entropy, where usually you would assume that the entropy would increase for a closed system of particles. However, if you have a bunch of particles that are gravitationally attracted to each other, what will happen is some of the particles will be thrown out to a larger radii, sometimes leaving, and some will be therefore condensed into smaller radii. So if you just look at the smaller ones, if you just look at stuff of the specific radius, things seem to get hotter, which is counterintuitive from the entropy and energy point of view. It's being paid for by stuff being thrown to infinity. So the center could heat up and the outer parts could cool down. So my understanding is, and this is what I was going to say last slide, that things like an elliptical galaxy has lots and lots of stars and is actually unstable to collapse. So an elliptical galaxy is very, very slowly collapsing, where there's many stars falling to its core. But the time scale for a collapse is many times the age of the universe, so they're not going to change appreciably over our lifetimes. At the same time, the galaxy is not just collapsing because that wouldn't conserve energy. The virial theorem wouldn't be happy, so there are stars being thrown out of it and thrown to much larger radii. A key statement is, for sufficiently condensed systems of particles acting gravitationally, the center will be unstable to becoming increasingly dense and hot, since that will decrease system entropy. A single temperature will no longer describe the system. Okay, another cool aspect of gravity is gravitomagnetism. That's a gravitational force that complements standard gravity like magnetism complements standard electric force. So if you just have a bunch of electric charges here, or even one electric charge, then you get force, electrostatic force falling off with r squared. Oddly enough, if you have a bunch of masses here, again, things seem to fall off as r squared. So it looks like there's an analogy, but we're going to get to that, I think, next time. That will be another slide on how good that analogy is. But still, if you move an electric charge, you get a magnetic field. What happens with mass? Well, it turns out that even in general relativity, there is something like magnetism. For electricity, it's called the gravitomagnetic force, not a force, phenomena in gravity, and it's even being searched for. There's a probe called Gravity Probe B that's orbiting the Earth and spinning and looking for a gravitomagnetic effect. However, it might be hard to tease the signal out of that. I think they're working hard to do that right now. This is typically a very small effect, whereas we use electricity to run appliances and things like that, and the electric force is much stronger per unit that we know of than gravitational force. So the magnetic force is much stronger than the gravitomagnetic force. So it's actually a very small effect. However, the sense of the effect that if two wheels are spun on a common axis, so here you have one, and here you have another, there's common axes going around like that, their mutual attraction will be slightly greater if they spin in opposite directions. Not something you really need to include in your average calculations. Your car tires aren't going to be attracted toward each other, less so, but it's something that's interesting. So a ring rotating around its minor axis, a circle inside the ring will accelerate matter through the ring while its matter feels no acceleration. Earth's gravitomagnetic acceleration at the equator is about 10 to the minus 7 Gs, which is hard to measure. This cannot be used to create a perpetual motion machine, unfortunately. So if you sit there and thinking, well, now we have something we can work with, no, it's not going to help. But it's complicated as to why not. Frame dragging. So another concept in gravity. So general relativity also expects this. This is a gravitomagnetic effect, but it's a very specific one. It's also known as the Lenz-Turing effect. So when a massive object rotating, if you go near a massive rotating object, you may feel that you are not rotating with respect to the universe, even though you can see that you are. So the analogy here is, let's say there's a black hole that's really zipping around here, spinning around really fast. So you're far away, and let's see. Let's undo that one because I can't draw a stick figure very well. So when you're far away from the black hole, everything seems fine. The black hole seems like it's rotating. Somehow you would know that. And you can look in the faraway stars, and your nearby gyroscope isn't precessing. So now you go close by. So you're near the event horizon of the black hole, or the ergosphere of the black hole, and you notice now that if you try to stay constant with respect to the distant stars, so that you're not orbiting the black hole, then it seems that locally your gyroscope precesses. Whereas if you work to make your gyroscope not precess, so it looks like you're back in an inertial frame, then it looks like you're orbiting the black hole. So that's called frame dragging. The frames are dragged along with the black hole. Again, this is a very small effect. Never been measured in the laboratory, difficult to do. One famous principle known as Mach's principle gets into this. If you were rotating a bucket with water in it, would it have the same effect as rotating the entire universe? So let's say you have a bucket here. Let's work this out. And in there's water. Now if you spin the bucket, then what will happen is you will see that the water will climb the sides of the bucket. So you'll know the bucket's being spun. But what about relativity? Let's say you spun the entire universe. Wouldn't that be the same? Well, people think that it actually would be the same. If you could spin the universe around the bucket, again, you would see the interior the water climb the sides of the bucket. This might not be relevant to almost any situation we can find outside in the astrophysical universe, but it might be relevant, in one case, to jets emitted from active galaxies. Jumping around, again, gravitational radiation. So, again, if you take an electric charge, say an electron, and you accelerate that charge, you're going to get electromagnetic radiation. Now again, going back to mass, If you take mass and you accelerate that, do you get something analogous to that? And the answer is yes. In general relativity, you get it too. It's gravitational radiation. So this is, again, very weak compared to photons. These things are all around us, though, gravitational radiation. Every time you shake your fist in anger at this lecture, you're generating gravitational waves. One of the big frustrations of modern science is that we haven't yet discovered firsthand gravitational waves. We've seen pulsars go around each other that are decaying as if they're emitting gravitational radiation, but huge gravitational detectors are being built on Earth, one of which is LIGO, and it is hoped that within the next decade or so that actual gravitational waves will be measured. These things should be emitted from supernovae, and we know what supernovae exist, and gamma ray bursts, which we know exists, but well, the supernova we know create neutrinos because we've seen that. So there's lots of reasons to believe that some types of supernovae would create gravitational radiation. Gamma ray bursts are a little bit more mysterious, but if there is asymmetric, then they might create gravitational radiation as well. Steady emission by binary stars, as I mentioned, so the binary pulsars, orbital decay can be attributed to gravitational radiation to high accuracy. So if gravitational radiation is a lot like regular radiation, it moves at the speed of light. So it has wavelength and frequency like light. Lambda is equal to speed of light, c, times frequency, f. Now, a passing polarized gravitational wave would have this effect on a ring of particles. So you have these particles all around in a circle, and the wave passes, and it causes a flattening back and forth. So again, it's slightly different. A lot of what we see with electromagnetic radiation is dipole-based, but gravitational radiation does not have dipole radiation. It's quadrupole. And what you're seeing here is actually a quadrupole. A dipole would be as if one side was bright and the other side was dim. Here, the top and the bottom are always the same. So what you're seeing is actually a quadrupole effect. And so this is my grab bag of things I wanted to mention but couldn't during the semester, mostly having to do with gravity. So actually, a similar lecture you might find having to do with quantum mechanics. But with that, I will close for this lecture and ask you to keep Schrodinger away from your cat. Thanks. Bye. Today, we'll be talking about different aspects in gravity. I call it potpurri because these things didn't fit into any lectures. So this lecture is being given near the end of the course, and there's little slides and things that didn't seem like they would make up a full 15-minute lecture. These have to do with gravity. So one is Birkhoff's theorem, which is really important. That allows us to do a lot of gravity and understand a lot of general relativity. So Birkhoff's theorem leverages usually spherical symmetry in general relativity and has two common applications. First of all, it says that so I put a bunch of them in here, so I'll be jumping from place to place here. Please bear with me, but it will be fun. There's some cool stuff here. So I am Robert Nemiroff. This is Michigan Tech, and this is an actual class at Michigan Tech. I'm an actual Welcome to Extraordinary Concepts in Physics, professor at Michigan Tech, sometimes called Physics X. So you can find these lectures, lots of these lectures, online or on iTunes by following buzzwords that you might find there. So let's get to some physics concepts. Most of